Okay. So today, as the last lecture, we will look at the uniform Turán density. And right, so as we can think of this, so these I would say are the three main variants of the hypergraph Turán density. And so the first one, the classic Turán density, is just the threshold in the edge density above which large k-graphs are forced to contain some copy of some small k-graph f. The second one was the threshold in the minimum codegree, and again formulated as density, above which we are forced to contain a certain k-graph f. And this one you can think of as the threshold in some form of local density. So what does local density mean? On every subset that's maybe not too small, but still pretty small subsets, we know that we induced on those, we also see many edges. Okay. So let's first define what it means. So for some density and some error term, so for today we'll just talk about three graphs, but all these concepts also generalize to larger uniformities. H is the beta dense if for all subsets U of the vertex set of H, we have the number of edges on U okay, so this is just the number of edges that H has on U. It's at least, so if we have this density, then what we would want would be D times the size of U choose 3. But because we want to see this as some form of quasi-randomness, so we want to allow some error term, in particular because we don't want this to hold for any arbitrarily small set. So that's why we allow this eta. Right, so essentially equivalently up to changing the constants would be that we say this property here should only hold for so maybe with some d-max epsilon should only hold for some sets which are at least of size some eta prime of the vertex. Oh, sorry, yes. Okay, and now we define the uniform Turán density. So we denote it with the pi with 3 dots, and this notation is indicating that there are also other quasi-randomness conditions, which we'll not study today, but which are also quite natural and for which you can then define the equivalent threshold, right? So then it would be a threshold for the density in that form of quasi-randomness above which you're forced to contain the K. So this supremum removable D such that all eta and n there is some F3 the interlens graph H at least n vertices. Okay, so because this definition is a bit long, but so even if you don't fully understand it now, maybe just try to keep following the proof that we'll see in a moment, because the concepts in there are still interesting, and we will also then will also allow you to some extent, for practical reasons, forget about this definition and think about different objects instead. Okay, but so still, I hope that you all agree that this is essentially what I said before. So the threshold in this form of local density above which we are forced to contain some k-graph f. Okay, because we need it for all error terms. Okay, so we can make the error term arbitrarily small, and still with a density we would want to contain an f. Okay.
So I guess everyone's shy in asking question. Let me ask one. Is this equivalent to XYZ, and then you have density P across XYZ? I see XYZ implies this version. How do you go the other way?
So again, you have to change the number of constants that that you know.
Even changing it, I don't see immediately.
And so once that we're
the quadratic definition is equivalent.
Right.
And we choose three subsets.
Three subsets.
I think it is not equivalent.
I think
because you can use the two larger disjoint complete three graphs. It satisfies this definition, but not satisfy.
Yeah, but I think for the density,
it is.
Yeah.
Yes.
Because but you can always go through regularity, right?
Oh. Mm-hmm. Okay. Yeah.
And yeah.
Mm-hmm.
So these problems, or this notion, was introduced by Yedish and Schoch. And they asked to determine this uniform Turán density of the K4 minus and the and so this, on the one hand, the idea was that maybe if we cannot do it for the normal Turán density, where we don't have any additional restriction on how the edges are distributed, maybe we can determine the threshold for this uniform density because we have a much stronger condition. But by now, this concept is also has become interesting by itself, and so it's not necessarily clear, given some specific f, whether it's harder to determine the codegree Turán density, the normal Turán density, or the uniform Turán density. And for instance, also Flank algebras tend to work less for these ones, even though so the progress was made after roughly 30 years, and first this one was proved, so was determined using Flank algebras. So this was by Glebov and Wolitz. And then after a little more time, Reyer, Rödel, and Schacht determined this again, but without using flag algebra. So in particular, this proof is human readable. And so what is the answer? Not that the answer itself is particularly important, but it's one quantity. And yeah, so but in general, this condition apparently translates, or it's harder to translate it to the condition that the kind of conditions that you can use flag algebras for. So let's first look at the construction. So let T be the random tournament or on n vertices. So that means for every pair, or every two set ij on our n vertices, we decide to take one of the two directions. So either from I to j or from j to I. And we do that independently for all the pairs, and with probability 1/2, we take either direction. Okay, so we just choose one orientation that independently refers to different pairs. Okay, and now why we so this thing is just a thing for graphs. Basically, we have our vertices, and now we place orientations for any two of them. And so, how do we obtain a hypergraph from this? This one will say then we have a three graph on the same vertex set. As STM and edges given by cyclic triangles. So if we see this or the other direction. Okay, so now we, on the one hand, we claim that this one is uniformly dense with density 1/4, and on the other hand, we claim that this APN is k for -3. So first, maybe let's check the k for -3ness. So if we would have a k for minus, then in particular, we have this edge. So I try to always think of the k4 with the apex in the upper left. So we have this edge, which means that the orientation of this one has to go either around like this, because it has to be a cyclic triangle, or around the other way. Okay, so without loss of generality, we can say that the orientation goes like this. Okay, so then also this here must be an edge. But this one of the edges, or one of the underlying pairs, is already oriented. So we know the orientation on this edge, which must be this. But now we look at the last edge, which, since this is the apex, is this one, and this one. But now this pair and this pair are already oriented in a way that tells us that we cannot see an edge there. Okay. On the other hand, Zuma have things. Shows. So why is Zuma have things? So think of normal concentration, but we cannot just apply the very standard chain of, because the events for when we have indicator variables for each edge to be present or not, so for every triple, then those are not independent. But with Azuma Höfting, we can control this kind of not complete independence. And so that shows that we are concentrated around the expectation, which means that we can show that for n getting larger and larger, asymptotically almost surely, we are dense on any not too small subset. And that means that H is, and okay, so what is the density that we expect? In total, we have 1/2⁵ possible ways to orient the 3 triples on our 3 vertices. And 2 of those, right, the 2 directed cyclic triangles, give us an edge. So we have 1/4 of edges that we would expect. So what we get is that we are 1/4 eta dense. But this is for every eta. So for every eta, we have that as n goes large, we're asymptotically almost surely 1/4 eta dense. Okay, and this implies and we are greater or equal to 1/4, because in here, right, so for all eta, we can make n so large that we know that this HTN is 1/4 eta dense, but all the HTN are K4-3. Okay, so in particular, those HTN will be candidates in here. Or, of course, those which because this is basically a family, right? Because it's just a random thing. But those which then satisfy this Switcher-most, they will be candidates. Okay. So for the upper bound, we need some preparation. And so this preparation in principle is a hypergraph regularity, but of course in one lecture maybe we cannot go through that. Also, how many people have seen normal graph regularity? So who has seen normal graph regularity? So many, but some don't seem very confident whether they've seen. But anyway, we will do it completely without that. But the motivation for the following objects come from hypergraph regularity. So they might seem a bit strange, but I still also encourage you to think of, as you can define some other combinatorial objects, so maybe matroids or something, you can also just define the ones that follow, and then you can just think about those. The reduced hypergraph and again, this is in principle a reduced 3 graph for us, and one can think of those in larger uniformities as well. But for today, we'll just stay in the 3 uniform world. So, okay, so A, we have an index at I. Then we have sets of vertices for each pair ij, and then we have a 3-partite 3 graph Hij for every triple of indices ijk. So where the ij is just some 2 set of the underlying index set. And 3 part-times 3 graphs Aj on but it goes this with vertex classes. So on this triple of indices, we have 3 pairs of indices, and those for each of those pairs, we have this class of vertices, and those are the partition classes of our Aij. Okay. And so how do we usually think of these? Here. So for the indices, we will just draw dots. So this is maybe I1, I2, I3, I4. And for these, which are sets of vertices, we draw just the line between the respective partition classes. And so now this thing, for instance, for I1, I2, I4, would be a 3-partite 3 graph with these 3 vertex classes. Okay, so an edge would be drawn like this, because we can take a vertex in this partition class, a vertex in this partition class, and one in this one. Okay.
How the notation itself really include that Ij are selected from I.
This one here.
Yeah.
Yeah.
This doesn't look like P12 to me, and somehow it should be formally written somewhere. You are enumerating from all the indices in time, right?
Yeah. Yeah, I mean, this is like the shorthand notation.
Right.
And okay, so now and this again, the motivation for this kind of objects is that essentially they capture what you get after applying hypergraph regularity. Okay, so similarly as for graphs, when you apply regularity, then you often talk about the reduced graph, where you place a vertex for each of the vertex classes, and you place an edge for every pair that has maybe some minimum density at least, and is regular. And this thing corresponds to the situation after hypergraph regularity, but because for hypergraph regularity, you need to be more detailed. You need to work with several layers, and that's why this structure is also more complicated than a simple hypergraph. Okay. Then we also say that this one, so the reduced hypergraph, A is D dot dense if all AJK we have that the number of edges in that particular tree graph is at least D times what we would expect. And what would we expect, or what's the total number of edges? The product of the size of the three partition classes. So P I J, P I K, P J. Okay. So in some sense, this tells us that each of these three-partite tree graphs has a lower bound on the density. But the density then is the normal thing for a three-partite tree graph. Okay. And lastly, we also need the right. So this is basically what that condition translates to. If you start with an H graph with a three graph, which is uniformly dense, you apply regularity. You can then construct from what you get out of regularity. You can get this reduced hypergraph, which is dense in this sense, with here the density that we put in the beginning. Okay. So now we need to define so similarly as for graph regularity, when you want to apply graph regularity, when you look at the reduced graph, you want to say, okay, which pattern in the reduced graph actually lets me embed whatever I want to embed using regularity, right? And that comes, the situation that you need comes from the embedding lemma. And again, for graphs, the embedding lemma and then therefore the reduced graph looks just like a normal graph. But here for the embedding lemma, for the hypergraph embedding lemma, we need a more complicated situation. For a tree graph F and a reduced hypergraph A, we say that lambda phi is reduced reduced image of F if and so for those of you who have seen hypergraph regularity before, you can now just check whether the conditions that I'm writing are the ones that allow you to use the embedding limit, because that's exactly what these conditions are for. They just tell you that when you have those situations in a reduced hypergraph, that reduced hypergraph came from what you got out of hypergraph regularity, then this reduced image will tell you that you're in the setup for which you can apply the hypergraph embedding limit. So the first thing that we want to have is that lambda should be the map from the vertex set of F into the index set of the reduced hypergraph, and phi should go from the shadow of F into the vertex set of our reduced hypergraph. Okay, so the reduced hypergraph as a hypergraph itself consists out of the union of all these three graphs. So yeah. Union of the vertex sets, all these P, I, J. Okay. Does everyone know what the shadow is? Sometimes also called skeleton.
You define Pij as vertices.
Sorry?
You already defined Pij as vertices, right? Set of vertices.
Yeah.
So you don't need put P.
Oh, sorry. Yeah, I meant to repeat. Does everyone know what the shadow is? No. So the shadow of a big graph F are just all the pairs which are contained in an edge. So if this is a 3 graph, then it's the xy such that the existence z such that x, y, z is an edge. So, for instance, for our K4 minus that we will look at in a moment, we have that every pair is in the shadow, because this pair is, for instance, contained in this edge, this pair is contained in this edge, this pair in this edge, and so on. So you just check whether a pair appears in some edge. The second condition then tells us that whenever we have some edge in our, or some pair in our shadow, then we need that the respective vertices get mapped to distinct indices, and the shadow edge gets mapped to the respective vertex class between those two indices. So all I all x, y in the shadow F lambda x is not equal to lambda y, and the phi of x, y is in partition class of lambda x lambda y. Okay, so between for any pair of indices, we have one of those partition classes, and we want to map the specific when some pair lies in the shadow, we want to map it to the respective partition class. And lastly, when we want to have an edge in F, then we must see an edge in the respective three-partite tree graph of A, right? So when we have an edge, in particular, each of the pairs in F will lie in the shadow. So therefore, we know that these vertices get mapped to three different indices, and we know that for each of the pairs in the shadow, we have the respective vertex in this vertex partition class between those two indices. And so we can ask for these three vertices to form an edge. So if x, y, z is an edge in F, then the phi x, y, phi x, z, phi y, z should be an edge in A.
Edge. Now that's super. That's now that I say that. I think it's correct.
No, phi maps phi
Yeah.
F.
That as well. Yeah.
Okay.
Okay.
Should be an edge in lambda lambda x lambda y. Okay. So if let's look at this for the K4 minus. So we want 4 indices because our K4 minus has 4 vertices, and any two form an edge in the link. And by this condition, that means that all the vertices should get mapped to different indices. So we want 4 indices: I1, I2, I3, I4, and then we also want to map all these all the shadow edges, which are all pairs of our on these 4 vertices. They should get mapped to the respective partition classes. So we have our partition classes here, and we now want to have vertices in each of these partition classes. Okay, and now let's say that the vertex that we mapped to here was the apex of the K4 minus. So now in our K4, we had in particular this edge. So this vertex get mapped to here, this vertex get mapped to here, this one get mapped to here. Then this pair got mapped to this vertex, this pair here got mapped to that vertex, and this pair here got mapped to that vertex. Okay, so because we see an edge here in our F, which is the K4 minus, we want to see the edge between the respective 3 vertices in our A, I1, I2, I3. Okay, so next, let's look at the let's look at this, the edge. So these vertices, we have for each of the graphs between, or for each of these pairs, we map them to a vertex here. So it's this vertex for this pair, this vertex for this pair, and this one for this pair. Okay, and again, since we see an edge, we want that those three vertices form an edge in our reduced hypergraph, in particular in that particular partite 3 graph. And lastly, we have this edge here. Okay, the vertices are mapped again. The pairs are now mapped this one to this one to this, and this one to this. So we also want to see this 3 edge. And maybe I can draw it in a dotted way so that we can still distinguish the different edges. Okay, so do we agree that this one is what we are looking for? And so what we have now is that instead of trying to determine this, we can also just determine the this density over all reduced hypergraphs, which are free of a reduced image of our F. So say that A is F3 if there is no reduced image. F. And the theorem by IM chart states that the uniform transidentity of F is equal to the supremal for all D, such that for all M, there is a an F3 D dense reduced hypergraph. With index set M. Okay, so let's see that this makes sort of sense with the caveat that I didn't tell you at all how the hypergraph regularity step works. So, okay, we're going over these densities. Then what I promised you before is that with hypergraph regularity, we can translate some d-eta dense 3 graph into a d-dense reduced hypergraph. And I told you that whenever we have a reduced image, then that allows us using hypergraph and the hypergraph embedding lemma to embed F into our H. Okay. So this is why it sort of makes sense that that now we can just consider this. So now, using this theorem, let's prove this theorem here. This one.
Analogy we should have in mind is this is kind of the homomorphic image in three uniforms, I think, right? Or
Yes, I mean, in a sense, but of course the going via the regularity step, right?
Yeah.
So we need this hypergraph embedding lemma. Because one can also talk about sort of just homomorphism Turán density, for which one doesn't necessarily need to apply the regularity. Okay, so first let's fix some hierarchy. So let M be the last constant that we choose. Then we maybe have some M1. And then our epsilon. And we can also assume that the epsilon is much smaller than 1. It doesn't change things. And so we already have our lower bound, right? So what we just need to show is that whenever we are above 1/4 by an epsilon, then we can find a reduced image. So you need to show that given 1/4 plus epsilon dense reduced the graph H A with index set M, we find a reduced image of F in A. And F being our key minus. And actually, let's still to maybe say where we are going. Let's look at this picture again. And so what we want here is some of the vertices look more complicated to find than some of the other vertices. Right, so this vertex, this one, and this one, they only lie in one edge, whereas the other ones lie in two. So what if we find instead, but using maybe blue, find appear here, and appear here in some auxiliary graph. And what should this auxiliary graph mean? We place an edge here in this auxiliary graph, whenever there exists an edge, a 3-edge, to some vertex down here. And replace an auxiliary edge here whenever there exists a vertex here. And similarly for here. Okay, so then so where would these graphs lie? So all of them have this index I1, meaning we are basically looking at a graph between the partition classes, this Pij, with I1 always being one of the indices. Okay, and then between every pair, we can define these blue edges. And in that multipartite, right, so we have basically the number of indices now as partition classes. And in that graph, we want to find a triangle, this blue triangle. Okay, so that is the idea. And but of course, to find a triangle in some multipartite graph, we need some condition. And the condition that we will get is a condition on the sum of the degree squared from one partition class to the next. And to derive that, we will use the Cauchy-Schwarz inequality. So that's basically the whole proof. But okay, so let's for I, J, K, index that where we have this ordering I, J, Q. Q, I, J, K, being the auxiliary graph with vertex and bipartite with vertex classes P on K and P on J and an edge from some vertex V in P I K to a vertex U in P I J, if there is some vertex W in P J K such that UVW form an edge in their respective AIJK. Okay, so what did we do here? We said, let's look at some IJK, and we want to define a bipartite graph between this set of vertices and this set of vertices. And we want to place an edge here whenever there exists some vertex here, such that this thing is an edge in the AIJK. Okay, so now let's also do that for the other direction here. So between this partition class and this partition class. Similarly, let Q, K, I, J be the graph on the set. So the down one and the upper right, so it's P I K and P J K. with V in PIK and W in PJK, forming an edge. If they exist now, right? So to define this one, we just draw this again. Place an edge here whenever there exists a vertex here, such that this forms an edge.
This is again just a shadow.
Sorry?
This is again just a shadow. You're just defining it through, you can just define through the shadow
The shadow of what?
of AIJK or an edge in AIJK.
Yeah, but we don't want this graphs, right? We just want like the shadow in one direction. So
Right, so the shadow splits into three vector graphs.
yeah, but we only care about two of them.
Ah, okay.
So yeah, if there is some U in EIJ with UVW being an edge in AIJ. Okay, so it's really, I mean, the words here might seem complicated, but it's not really complicated. We just say for one graph, we want to look at all the pairs here for which they exist a vertex here such that they form an edge, and the other one, all the pairs here for which they exist a vertex here such that they form an edge. Okay, maybe because I have the pictures there, I will move to here. Okay, so what can we notice now? By double counting, we have, if we maybe draw one more of these where we now just place the blue edges. We look at a fixed vertex down here. And we look at the neighborhood on the left in the neighborhood on the right. Now, the number of edges that the vertex in the bottom is contained in is at most the product of these two neighborhoods, right? Because we see a vertex in the neighborhood if it lies in some edge. So the other vertices are not contained in an edge. So at most, we have, for this vertex, all three edges taking one vertex here, and this vertex itself. Okay. We might not have all of those, but that's an upper bound. So we have that the number of edges in this is at most the sum over all the vertices in PIK, the degree with respect to this QIJK of X times the degree with respect to QKIJ. Okay, then here we know that we have the lower bound of 1/4 plus epsilon PIJ, PIK, PJK. Okay, this lower bound is because our reduced hypergraph is dense and 1/4 plus epsilon width. And this upper bound comes from the fact that all edges must use one from the neighborhood in this graph and one vertex from the neighborhood in this graph. And then we just sum over all vertices. Okay, so by convexity, by Cauchy-Schwarz, we get that the right-hand side is bounded from below, from this side is bounded from above, by the square root of the products of the sums over the squares. So d qi jk x squared times the sum d q k I j x squared. And the sum still going over all x in. Okay. So this means that one of these sums of the degree squared will be large. And why is that nice? Because I told you before that eventually what we want is we want to find a triangle in this auxiliary graph here. But then I also said that to find a triangle, we of course need some sort of condition. And that degree, that is how we get the degree condition. Thus, any ijk we have one of the following. So the first is maybe that this is large. And what does large mean? So since we multiply these two and then take the square root, we get that one of them needs to be more than 1/4 plus epsilon, and then some parts of these. So 1/4 plus epsilon. And what we would like to see here, and that will work, is that we essentially take the PIK, the size of PIK, and then because here we square this, so we want PIJ, the size of that squared. Okay, and the other the other thing that might happen is the sum q k I j x squared 1/4 plus epsilon, and then here again PIK, but then this one PJK squared. And to check that one of these must hold, you can just say, okay, assume that this one is less, this one is less, then the product of them is less than this times this, and then the product of each of these squared. But then we take the square root, and it needs to be larger than 1/4. So okay, the product of these will reduce again to 1/4 plus epsilon, and the product of all of these squared will go to this one. Okay, so if both of these are smaller, then this thing would be smaller than this thing. So now basically we have a degree condition, but note that the graph that I suggested in the beginning, this blue auxiliary graph, actually consists out of maybe this QJKI, but of many of those where we fix the I and then we want to look at many different JK. So, but now what happens if sometimes this occurs and sometimes this occurs? But for such issues, we have Ramsey's theorem, which allows us then to just sort of clean this out and we can get that always one of the two has to occur, because we can think of these two cases as colors on the triples. Right? For each triple, we color it with 1 if case 1 occurs, and with 2 if case 2 occurs. So Ramsey's theorem applied to case 1, case 2 coloring. All triples. Gives a set of M1 indices. Right, so this is why it shows why we chose this hierarchy. Right, we have the M is much larger than M1, so that we can apply Ramsey. And without restriction, these are just the first indices, just so that we can write the index set easily. But then, for all ij in M1, the same case occurs. And without restriction, let's say it's the first one. Okay. So now let Qi bar be the union of all the Qi jk. For I being maybe right, so this condition tells us that because we had this ordering all the time of our indices, so we have now this condition whenever I smaller j smaller k, and so that means that if we write here our p M1 maybe P1 M1 P1 M1 minus 1 P1 M1 minus 2 and so on. So always the index 1 and then the other indices in decreasing order. Then when we apply this condition, right, always for our I equals 1 fixed, then we know that the degree, right, so this degree went from the IK index class, which is the one using the smallest index and the largest index. So for the first one, this one's the smallest and the largest, because somewhere later here, we will see the smallest, namely 1, and the second smallest, or the intermediate one. So our M1 is like K, and then somewhere in here, the second index, for instance, with M1 minus 2, that would be the J. And our I is just 1. So that means that we have this degree condition from here to here. We have it always from one of the vertices here to the right. Okay. note that Q1 bar is the with partition classes. P1 and 1 down to P1, 2. So this is M1 minus 1. And if we call these V1 to Vn, the degree condition that for all, let's say J smaller k, the sum of the degrees, when we look into V k, and we take the sum of the degrees squared from the sum over all vertices in Vj, then this is greater or equal to 1/4 plus epsilon times the size of Vj times the size of Vk. Okay. Because we have them ordered in this way, and because we always have with our I smaller j smaller k this condition on the degree squared, it translates to this kind of graph. Okay, so now for all of those who fell asleep, now it's time to wake up, because now we're just talking about graphs, and the proof for the following lemma is also quite beautiful.
How do I read this sentence? Now let Qi bar be the union of Qjki for I equals 1. No.
And yeah, so this is for all ij, right? The union of all these, and no, for all ij. And then I'm saying that actually we just want to take I equals to 1.
For all JK.
For all JK, yes, it's true. Yeah.
So question is that you see always for case 1, but here is case 1 is PIK times PIJ square, but here is VJ OJ times VK square.
Yeah, because the one further to the right is smaller in terms of the indices.
Oh yes, which changes the order.
Yeah. So we will now finish with the following lemma. Right? The following lemma will tell us that for this kind of graph, if our m is large enough, and we can make the m large enough because it's just that m1 minus 1, we can always find a triangle. So let G be an m-quartate graph. But, let's say for every epsilon greater than 0, there is some m such that if G is an m-quartate with non-empty partition classes
Wait a second, so how do you define the V1 to Vm? It's just M is equal to big M1 minus 1.
Big M1 minus 1, yes.
Okay.
And I'm just renaming them. So that I don't have to write so much here. With non-empty partition classes. V1 to Vm and the following condition. So when we sum over the degree squared over some partition class Vi, then by dj I just denote the degree into the partition class Bj. Then this should be greater equal than 1/4 is epsilon times the size of Vi times the size of Bj squared for all I small j. So we have this M such that if G has these properties, then G contains the triangle. Okay, so that's exactly the setting down there that that we wanted, because now a triangle, right? A triangle in this blue graph here. Let's say that we see a triangle here. Then, by definition of this blue graph, this actually meant this blue edge here means that down here we also have our partition class M1 minus 1 M1. And we see some edge like this. And similarly, we have the partition class here, the one with M1 minus 1, M1 minus 2. And we see this edge. And then we have one with M1 minus 2, M1. I don't want to draw it, where then this edge unpacks into a 3 edge. Okay, and that, as we still see here in this initial picture, that gives us the K4 minus. So once we have this lemma, we are done. Okay. So how do we prove this lemma? Okay, so first we want to determine sort of the effective maximum degree. So meaning that for any two partition classes, we want to say what is the maximum degree that still occurs quite frequently, right? There might still be a few vertices which have larger degree, but effectively the maximum degree will be what we will determine. So for I smaller j, and so being indices here, and R and N, define the set R by J R as the number of those X in Vi for which the degree into the partition class J is greater or equal to 1/2 plus R times delta of what we would expect. Okay, so why do we suddenly see 1/2 here? We're talking about the degree, right? And if the sum of our degree squared is greater or equal to 1/4, then we would expect that as sort of, if we just everything was average, the average degree would be 1/2. And let Rij be the maximum R, such that this set still has reasonable size. And by reasonable size, I mean delta P large. Okay. And I didn't tell you what the delta is. The hierarchy that we want to look at is we're given some epsilon, then much smaller we want to pick our delta, and then much smaller than that we want to pick some m1 minus 1, and much smaller than that we want to pick O. Okay. So in particular, this tells us that that we can actually pick this minimum R, because if even the for R equals 1, this set was so small, then we get a contradiction to our degree condition, because that would mean that essentially when summing over the degree squared, we could not get above 1/4 plus something depending on delta, but delta is much smaller than epsilon. Okay, so that tells us that definitely this first set for R equals 1 must be at least of size delta. And then note that these sets for increasing R, the sizes of these sets are decreasing, and definitely they are empty once R reaches something like 1/2 delta. Because for 1/2 delta, this thing is just, or for larger than 1/2 delta, this thing is larger than 1. Okay, so we can pick this maximum R. And now we're again left with the issue that for the argument that we want to make, we actually want to have that that this effective maximum degree is the same between any two pairs, right? But we just saw how we deal with this kind of problem. We just color the pairs Ij with respect to what this maximum thing is. And then we find some maximum and some smaller number of indices, this M1, such that we can still, such that we always know that this is the same. So, such that Rij is the same on Ij M1 to I small j. Okay. So and let's say let R star be this one. So why am I calling this effective maximum degree? We now know that whenever we look at two partition classes, VI and VJ, VI and VJ, we know that for most of the vertices, the degree from here, so for most of the vertices here, the degree in this partition class is at most 1/2 plus R star times delta, and that whole thing times the size of VJ. And there are a few exceptions, but those exceptions are very few in the sense that they're at most a delta proportion are set. That's why I'm saying that this is the effective maximum. Okay. So now, now note that since our M1 is still very large compared to delta, we can pigeonhole over these sets R1J. So we just look at the first of our partition classes, and then the set of vertices in this partition class with respect to the partition class further to the right, the set of vertices which have large degree, which have this effective maximum degree. Okay, so we have our partition classes. Here's V1, and for each of these sets, we know that we have some set here, which is of size at least the delta proportion of V1, such that the vertices in here have all large degree into this partition class, and we have this one would be R1. Let's say this is J, R1J, R star, and we have this set for each of the other ones. If this is J prime, we also have here R1 J prime R star. But since we have so many indices, we have many sets here, right? We have our M1 indices, and maybe one of them is 1, but since we're much larger, and since each of these sets is a delta proportion, by pigeonhole, we know that 2 of them must intersect. Indices, say 2 and 3, such that R1, 2 R star intersects R1, 3 R star. And maybe we pick some vertex X in this intersection. Okay, so how do we finish then? Let's draw yet another picture for this situation. We now have our X. We know that this X has large degree here, namely this 1/2 plus R star delta times V2, and also large degree in the bank. And any edge that would go from this neighborhood into this neighborhood would give us a triangle, which is what we want, which would let us finish. So we know that if we don't have a triangle, then we cannot have any edges here. But now we just count this sum of the degree squared on which we have our condition. So we sum the degree squared and we divide the sum into the vertices in here and the vertices in here. So for the vertices in here, our degree is bounded by this thing, which is small, and especially if r star gets larger, it gets small. The degree of the vertices here, apart from maybe some exceptional set, maybe there's some bad set here, for which, but this set, so for which the degree is even larger than the degree with r star, but we know that such a set would be of size at most delta. In delta proportion. So that's why these cannot contribute to this sum by a lot. But for all other vertices, the degree to this side is bounded by the effective maximum degree, namely this 1/2 plus r star delta. Okay, and in particular, if our r star gets smaller, then the bound on the degree of the vertices here gets better. So what I said before is that if our r star gets larger, then the bound on the degree of these vertices is better. And if it gets smaller, the bound on the degree of these vertices is better. And as it turns out, this gives that for each r star, we will get a contradiction if we don't have a blue edge in there. And because the calculation is actually quite simple, let's maybe do that. So let A2 be the neighborhood of x in B2, and B2 be the remaining thing. So this is A2. This remaining thing will be B2. And similarly for A3 and B3. Okay, so if G does not have a triangle, so our 1/4 plus epsilon V1, V2, V3 squared, which is the lower bound on the sum of the degree squared over all vertices in V2, the degree squared taken in V3. This is at most, so as I said, we split this sum into our vertices which lie in this A2. For those, the upper bound is the complement of A2, which we called B3. So B3 is at most 1/2 minus r star times delta times the size of B3. And then we sum over the vertices in B2 minus the exceptional vertices. So B2 minus R2, 3, R star plus 1. Right, these are the exceptional vertices, the ones for which this degree condition is, or the degree is greater or equal to 1/2 plus r star plus 1 times delta. And because they nested, right? So it's not that these are only those of a specific degree. So this, okay, for all these, we have the effective maximum degree as a bound. And then we have the exceptional vertices, which are at most this many, and for those we don't have a bound, and we need some squares. So here we get this squared, and here we get this squared, and this squared. Okay, and so now if we have this, note that A2 plus B2 sum to the whole set.
I think that should be 1/2 plus r star plus 1 delta. No?
Here?
Yeah.
Oh, yes, yes. Yes. So since this set and this B2 set sum to the whole of B2, we know that this term gets maximized because this factor here is smaller than this factor. So it gets maximized if A2 is as small as possible and B2 is as large as possible. So, but A2, because it's the neighborhood of our vertex X, which was one of those large neighborhood vertices, so it's at least 1/2 plus r star plus r star delta times B2, and then we just have this r star delta squared, 3 squared, and this was is in this case, if this one's as small as possible, this one as large as possible, but that's still just 1/2 minus r star delta B2. Okay, so now let's definitely cancel out this part and also the V2 part. Okay, now what we are left with are these terms with the 1/2, which roughly go to 1/8 here because we have the squared, and 1/8 here with the squared, and then these r star delta terms. And you can make the calculation that this gives a contradiction because our delta is much smaller than the epsilon. Okay, and that's the proof. And again, this gives us a triangle in this auxiliary graph, but the triangle in that auxiliary graph, still have the picture, gives us the reduced image of the alpha minus. Okay. So maybe some philosophical remark. So we've seen these 3 variants of the Hypergraph Turán problem, and one interesting problem, and that's the problem that has mainly driven the progress so far, is to determine one of these variants for some specific f, right? But we've also seen one result in the first lecture that was a bit different, right? That we characterized all those K-graphs which have Turán density 0. And generally, this kind of result gives us some information about the general distribution of Turán densities, or some variance of these, in the interval 0, 1. And that first result, as I mentioned back then, it actually tells us that we don't have any Turán densities between 0, strictly between 0 and k factorial over k to the k. And for this Turán density, for this uniform Turán density, we also have such a result. So we also have a characterization of all the three graphs which have uniform Turán density 0. And for the codegree Turán density, we don't have such a characterization yet. And even a more striking difference is that the characterization here also implies a gap. So again, our uniform Turán density for three graphs is either 0 or at least 1/27. For the codegree Turán density, that's not true. So for the codegree Turán density, you can have arbitrarily small densities that occur. And I think that in the recent years, there has been more progress towards these kind of general statements about the distribution of these. So yeah, for instance, also result by Ding, Liu, Wang, and Yang is that the codegree Turán density being 0 implies the uniform Turán density being 0. So we also have some relations between these different densities, but there's still even more that we actually don't know. So a lot to work on.
Yeah, let's thank Bjarne.